one, go.
Well, let me apologize for this strange presentation of the talk. Had a kidney stone, and travel is not a good idea when one is sometimes subject to such pain. What I'm going to talk on today is mathematical textbooks. There are a number of things one should be able to expect in mathematics textbooks. First, the mathematics should be correct and set at an appropriate level. Second, advice to students should be sensible and not mislead them. Third, the author should know what students know and know what they will learn in some later courses so that what is included builds on what has been done before and helps lay a solid foundation for future work. Good problems are also vital. Well, it will likely come as a surprise to students. Teachers should know that it often happens that an idea that's introduced to solve one problem turns out to be very useful in solving other problems, sometimes seemingly unrelated, and over a large number of years. Much of this talk will focus on one idea, but before we get to that, we have to do some background. Right triangles are going to be used regularly, so it is important for students to learn how to make a right angle. Have them tear out a blob of paper and fold it twice. Can you stop for just a second? So you take a sheet of paper and tear a blob out and then fold it to get part of a straight line, and then fold it again to get a right angle. It's much better for students to do that than to use the corner of a sheet of paper as a way of using a right angle to measure an angle, because they get some feeling for what a right angle is, and that it's half of what we call a straight angle. We're going to deal with area, and we're going to eventually get to a picture for the area of a triangle, but area starts with a unit square and then builds up from that. You build up first to rectangles, and then rectangles that are put together, as in this picture, where you have two 4x3 rectangles that are put together. And so the total area is going to be the area of each of the two rectangles separately, then added. But then students should see how you can do some mathematical reasoning with basically the same picture, but now being given 7 units in the bottom, but not then this unit up here, but 4 here, so this is going to be 3. And you had 4 pieces of information there. We have 4 here, that's a 1. And 1 from the 4 is going to be the 3 here. You have to then draw an auxiliary line, which you can draw as up here, or you could have drawn it across this way, and then had a rectangle that is 1 by 3 and then 4 by 7. After doing rectangles and seeing how they can be put together, we want to get to the case of a triangle. And it's very useful to start off on grid paper. But the picture that we're going to draw here on grid paper, and this is not the first picture. The first picture should come as a 1 by 1 square that you cut in half with a diagonal, and then a 2 by 1. You see that the two triangles that you have gotten by drawing the diagonal are congruent. They're the same. I like to illustrate this with students by pointing out the difference between a triangle and a quadrilateral. A triangle is rigid, and you can see that by looking at a triangle that you can form with your fingers, and you have, say, 3rd grade students do this, and then have them move it around, and no matter how you do that, it's the same triangle. But then when you start with a quadrilateral, you see it's flexible. And so when you know 3 sides of a triangle, you really know the triangle. Later on that should be proven, but it should be used earlier than that. And it's used here to get the area of a triangle. And then you draw the same type of picture without the grid, a base B, a height H, and you draw a rectangle completing that right triangle to make a rectangle out of it. And again, the triangle is half the area of the rectangle. Then when you go beyond a right triangle, you want to consider a general triangle, and we'll talk about the problems that exist in doing a general triangle in a while. You all know that the formula for the area of a triangle is half the base times the height. And the 1/2 could either go with the height, or it could, in fact, seemingly go with the base. We want it to go with the height. You can look at the following picture. Halfway up the sides, you draw a line across, and then drop a perpendicular from A down to that midline that you've drawn. And then on this little triangle up here, make the rectangle, and then slide the rectangle down to here. The same thing over here, sliding down to here, and you end up with a rectangle. The base I called A, the height is half of H. That's again a theorem that will be proven later on, but it's sort of intuitively clear that if you cut this side in half, you're cutting the altitude in half also. And the area of that rectangle is a half AH. That's the argument that's used in Singapore books. It's not really good enough to handle the general case, but this argument is, if it's modified slightly. This time we draw the altitude all the way down from A to the opposite side. And then we have complete the triangle to get a rectangle. And we have the same picture that we had before. And this rectangle, the diagonal cuts it in half, and this cuts it in half. And so the area of this triangle is half the area of the rectangle. Again, that isn't quite good enough to do the general case, but we'll see later on. What do I mean by the general case? Well, it is possible that there's an angle bigger than 90 degrees at the bottom, and then both of those proofs fail, but one of them can be modified to work. And that picture of dropping a line from a vertex to the opposite side of a triangle is the picture we're going to use time and time again. Now, the other quantitative result in primary school that is very useful for giving students good problems, or it's one of two other results, is the sum of the angles of a triangle. Usually this is introduced by tearing off the corners of a triangle and fitting them together. Now, this is not mathematics, because mathematics involves reasoning. And there's no way of taking that and making a mathematical argument of it. There are other arguments that are not quite proofs yet, but become proofs when students learn more. But here's one that uses nothing more than what we've used so far. Let's take the same set of pictures that we had before and start with a right triangle and complete it to get a rectangle. And again, we've cut the rectangle up into two congruent triangles. The rectangle has 360 degrees, 4 times 90. And so each of the right triangles has 180 degrees in the angles. And then for a general triangle, we drop a perpendicular from a vertex to the opposite side. But this time, unlike the case of the area, where we're not free to choose the side that we want, because we want the formula to work no matter what side we're taking. The final answer doesn't depend upon the side, so we can use the longest side, and so when we drop a perpendicular, it comes down and hits the triangle. And we then have 180 degrees in this right triangle, 180 in this triangle, and 180 down in the two right angles there, and so 180 in the angles around the general triangle. Now another result that's very useful when you get to interesting problems is what happens when you have an isosceles triangle. An isosceles triangle is a triangle where two of the sides are equal, marked here. This is from the second half of a 5th grade book in Singapore. What they do is they fold the triangle in half. Basically, you're cutting the angle at the top in half and fold it over. The center line is the same on both. These two outer sides are the same, and so they're going to have the same length. And you end up then with a triangle with two sides and the angle in between. And you can also see that that is a determining condition for triangles to be determined. And if that's true, then each of these individual triangles is the same, and so these two angles at the base have to be equal. And then there's a converse of that. If the two angles are equal, then the triangle is isosceles. The opposite sides are equal. That's 5th grade, and it's quite appropriate that they do it without talking a bit more about the reasoning for it. It is mathematics because the reasoning is all implicit there and can be made explicit when students have learned a little bit more. This is from an 8th grade book in Australia. Isosceles triangle, they give a meaning for what isosceles comes from the Greek, two sides being equal, and then proving the general result. And they say, notice that the proof is based on congruent triangles. The base angles of an isosceles triangle are equal. So you have CA and CB having the same length. You want to prove angle A equals angle B. Draw a bisector of angle ACB and let it meet AB at a point M. Then you had CA equals CB, CM equals CM because it's the same side, and the angles at the top were the same because of construction. And so from a theorem that has already been proven that when you have two sides and the included angle, the triangles are congruent, then matching the angles in congruent triangles, angle A equals angle B. In the next page in that book, they give a proof of the converse. Here is half of the Singapore book, 96 pages, and some of you have seen these books already. They're not cluttered with a lot of extraneous pictures. The pictures that are there are all relevant to the mathematics. There are little figures that often give you a piece of mathematical information. I was in the process of mentioning a few things about this Australian book when we ran out of time on the
memory card.
So you notice again there are no extraneous pictures. It's somewhat longer than the Singapore book, but the secondary Singapore books are somewhat longer. Those of you who know the secondary Singapore books will notice that this is a bit more formal than the Singapore books. I think appropriately so. Now there's one other result that I want to mention before we get to see some examples of problems. And that's when you have a pair of parallel lines cut with transversal. The angles, alternate interior angles are equal. And this is often just stated. You might have this on overheads and move up so that angle B comes up here and you see they're the same, and this plus that is the same as this plus that, so A equals B. But you can give an argument that is exactly the same as we've done before. Drop a perpendicular from A down to the second parallel line and from B up to the, and you've constructed the same rectangle that we have with the diagonal, and so these two angles, being corresponding angles in congruent triangles, are equal. Now here's a number of problems in which these different things that we've talked about are useful. First one was in the Tim's video, Japanese lesson. You were given angle A and angle B. They were given them as numbers, but it's exactly the same argument. And you're asked to find the angle X, and these two lines are parallel. And the students were asked to come up with a number of different ways. One way is to draw a line through angle, the vertex at X, parallel to those lines, and use alternate interior angles. Another is to extend this side up from B, and B and this interior angle up here are equal, and those two angles plus this one are going to be 180 degrees, and X plus this one is 180 degrees, so X is again A plus B. And the third way is you can drop a perpendicular from here up there, and you have a quadrilateral. Each of those, and that consists of two triangles drawing this auxiliary line. 180 here, 180 there, and well, this quadrilateral has 360 degrees in it, and we'll get to something like that a little bit later. The second problem was a 6th grade exam question on the primary leaving exam in Singapore. You're given a square and you're given an equilateral triangle, one side of the equilateral triangle being the side of the square, and you're asked to find the angle AOB. Well, what isn't completely obvious to students, but if they've been doing enough multi-step problems, they realize that you probably want to use all the information. This side and this side are equal, and so this is an isosceles triangle, so these two angles are the same. This angle is 60 degrees because of the equilateral triangle. This one is then 30, and then each of these two is 75. And since this is 75, and you have a right angle up there, this is 15, by symmetry 15 here, and you have 150 there. That's a nice class problem, and I'm amazed that they're able to put it on an examination, but they put a few harder questions on the examination so that students know that they ought to be working with some of the harder problems. And then a classic problem, a 5-pointed star. This is in the 6th grade Singapore book, 7th grade Japanese book, maybe it's 7th and 8th. In the two, but no, it's 7th grade in Singapore and 8th grade in Japan. You want to find the sum of the pointed angles at A, B, C, D, and E. And the only thing that you have to work with is the fact that the sum of the angles of a triangle is 180 degrees. And there are 3 triangles that contain the vertex A. One of them, this little triangle here, another one, this triangle, and then a third one, this triangle. And those two are done similarly. And then it's a matter of working your way around the figure. You want to eventually find out how many degrees there are in this pentagon in the middle. And you draw in those two auxiliary lines, and you have 180, 180, and 180, and those are all angles that are part of the pentagon, so it's 3 times 180. The top problem was in an old US book, and I'll say a little bit about something else in that book on the next overhead. There's a converse to that. If X is equal to A plus B, then these two lines are parallel. And it's interesting to have students come up with different ways of solving the original problem and then seeing how those different ways work to prove the converse of it. Now from that book by Durrell and Arnold, it's not the Durrell that's the famous Durrell. He was an English teacher, textbook writer, but an American with the same last name. 5 suggestions on how to draw auxiliary lines in rectilinear figures. A line connecting 2 points. A line through a given point parallel to a given line. We did the line connecting 2 points when we did the pentagon. and breaking it up into triangles, and earlier than that a quadrilateral. A line through a given point parallel to a given line. Well, we did that on the two parallel lines cut by two transversals. A line through a given point perpendicular to a given line. We did that here. A line making a given angle with a given line. We haven't done that yet, but there's a very nice use of that in Ptolemy's theorem, which I'm not going to be getting to. And then the line produced its own length, or more generally, extend a line segment. And that was also done here. There are times when you want to extend a line, it's just exactly its own length, but I'm not going to talk about one of those here, but it can be quite important stuff. Okay. Now we're going to skip into high school. A little bit in lower secondary. There you have a triangle we said before was a half the base, which I called A here, times the height H. After we look at right triangles and do a little bit about similarity, you can show that in two right triangles that are similar, the ratio of the opposite divided by hypotenuse is going to be the same for the two triangles. And we define that to be the sine of the angle C, and so we can rewrite the area formula in terms of the sides in an angle, which is a more useful formula than in terms of one side and a height. Now, just a word of warning. Congruence comes first and then similarity. Congruence means that two figures are congruent if basically you can move one and put it on top of the other to be exactly the same. And the moves are translations, rotations, and also reflections. And then similarity, two figures are similar if there's a dilation of one of them, multiplying the distance between any 2 points by a common constant, so that the two resulting figures, one of the original ones and the new one after you've dilated it, are congruent. We have programs that define similarity as same shape but not necessarily the same size, and then get congruence as a special case of similarity. And that shouldn't happen. Now we're going to use the same picture. Draw a perpendicular from one side down to vertex to the opposite side. Again, label that height H. H is A times sine of B in this triangle, and it's B times sine of A in this triangle, and so the two are equal. Sine A over A is sine B over B, and by symmetry, sine C over C. Again, there's the problem of what do you do when you have an angle that's bigger than 90 degrees, and we'll say a little something about that in just a minute. There is a fourth fact that should be included in the law of sines, is in East Asia, but has not usually been included in the United States, which is you take the circle that contains the vertices A, B, and C, and you put the diameter of the circle into this. The law of cosines, where we're using the Pythagorean theorem. The Pythagorean theorem, by the way, also follows from the same picture. C squared is H squared plus A minus U squared, and multiply it all out. H squared plus U squared is B squared, so C squared is B squared plus A squared minus 2AB. Getting rid of the U in this triangle, you have cosine C times B. And now, finally, let's get to the case of what do you do when the angle is bigger than 180 degrees? Well, with respect to the area, it's no real problem once you have the distributive property. You notice initially we didn't use the distributive property explicitly. It was there geometrically. But later you get it explicitly, and then the area of the given triangle ABC is the area of the larger right triangle minus the area of this new right triangle we've drawn in here. And that's h times u plus a over 2 minus h times u over 2, which is h times a over 2. The same thing works for the law of sines, except we haven't yet defined sine and cosine beyond angles of 90 degrees. But here's how you do it. C squared is a plus u squared plus h squared from the Pythagorean theorem. And again, h squared plus u squared is b squared, so we get a squared plus b squared plus 2au, and that's cosine of pi minus c in this little triangle right here. And cosine of pi minus c we're going to define to be minus cosine of c. And that's when you get to the unit circle, and you see that sine of pi minus c is going to be the same thing as sine of c, but the cosine has the opposite sign, because the sine is up above the x-axis in the second quadrant, and the cosine is to the left of the axis. Now, the crux of trigonometry is not the law of sines and the law of cosines. They're both useful. But the crux of trigonometry is the addition formulas. So, I want to show you a proof of the addition formula. The first time I've seen this historically is in a book by Davies in about 1854. It probably predates that, but I haven't found it earlier than that. I saw it in a video that Tom Apostol made on trigonometry, but wasn't smart enough to realize how important it was. And then it was a trigonometry book that Gelfand and Saul wrote that really called this to my attention. You can get you get the addition formula for the sine by exactly the same argument. The area is a half AB times sine of A plus B when you put these two triangles together. But it's also the area of the right triangle on the left and the right triangle on the right, so it's a half AH sine A plus a half BH sine B. And then you remove the h from both of these by using the other triangle. H is b times cosine of b, and a times sine of a, or cosine of a. And then equating, getting rid of the half ab, you get sine of a plus b is sine a cosine b plus cosine a sine b. Now I want to give you a quote from a pre-calculus book written in the United States, published in 1980, and I will mention something else from that book in a minute. In general, I'm not going to be mentioning the authors of the books, but this is an author who has a lot of influence in certain circles in mathematics education. How to remember these formulas? These formulas were the addition formulas for sine and cosine. Mostly you just have to remember them, because learning the proofs is certainly worse than learning the formulas. I have no idea why anybody would suggest to students that learning proofs is not important. And this proof is so simple. The proof that was given in the book is the usual one about rotation, which I have heard was due to Cauchy, and that seems reasonable. Now I want to end with some comments on trigonometry from textbooks. This is from a textbook for course for teachers. All the mathematics that a secondary school mathematics teacher needs to know. A common mistake that students make is illustrated in the following, quote, solution, unquote, to show an identity is valid. Example 11.26. Show that 1 minus cosine x over sine x is sine x over 1 plus cosine x. Students' mistaken solution. Cross multiply, or equivalently multiply both sides of the equation by sine x times 1 plus cosine x to get 1 minus cosine squared x is sine squared x. which we know is true since sine squared plus cosine squared equals 1. Done. So what's wrong? The student is using the fact that both sides of an equation can be multiplied by the same quantity. But we do not know the result is an equality. That's the point of the exercise. So when you multiply both sides of the equation, in quotes, sine x times 1 plus cosine x, you are assuming that they are already equal. That is, you are assuming what you are trying to prove in the proof, and that's illegal. I want to read a few more quotes on identities, and then go back and tell you what should have been said. From a book published in 1980. It's tempting to start with the given equation and then work on both members until you have reduced the equation to an obviously true statement, such as cosine x equals cosine x. What this actually does is prove the converse of what you were asked to prove. That is, if the identity is true, then the reflexive property is true. This is circular reasoning. It's dangerous because you might actually prove a false identity by taking an irreversible step, such as squaring both members. Yes, that's true. You could do something false if you do something that's irreversible, but the same thing is true with respect to equations. And here's another comment. Proving that something is in fact an identity is called verifying the identity. In order to do this, we have to work separately with the expressions on either side of the equal sign, and somehow show that they're equal to one another. The problem is that an identity looks very like an equation. Both have an equal sign between two expressions. And so it is very easy to slip into doing things that are okay for solving equations, but not for verifying identities. For example, in solving an equation, we frequently move things from one side of the equation to the other. But when we're verifying an identity, we're trying to prove that the two expressions on either side of the equal sign are identical. We can't possibly do that if we move things from one side to the other. Again, in solving an equation, we often multiply both sides by some quantity, but in verifying identity, we can't do that, as it changes the values of the expressions that we're trying to prove equal. That's a little bit worse. Caution. It's incorrect to work across the equal sign. For example, do not cross multiply. To do so assumes what is being proved is true. Well, no, but that's another story. We'll talk about that in a minute. Verifying, that was 1992. The first two were from 1980. The last one is from 2007, and I could have had others in between. Verifying trigonometric identities is a useful process if you need to convert a trigonometric expression into a form that is more useful algebraically. When you verify an identity, you cannot assume that the two sides of the equation are equal, because you are trying to verify that they are equal. As a result, when verifying identities, you cannot use operations such as adding the same quantity to each side of the equation or cross multiplication. Well, all of those are nonsense, patent nonsense. Here's what should have been said. When trying to learn how to work with trigonometric expressions, you often want to change one expression into another expression. Now, for example, the one that was given here, 1 minus cosine x over sine x is sine x over 1 plus cosine x. If you let x go to 0, 1 minus cosine x goes to 0 and sine x goes to 0. And so you don't know what's happening as x gets close to 0. But sine x over 1 plus cosine x goes to 0 divided by 2, which is 0 as x goes to 0. So the right-hand side is more useful than the left-hand side for the problem of finding out how does this function behave when x is close to 0. And so your goal in doing this is to simplify an expression. But students who are just learning a field don't know what simple is. And so they're given the other side to give as a goal to reach. Now, students should try to simplify it by working on just one side. If you can, great. If you can't, you solve the problem any way you can. And you can use any operation that's reversible. So when they were saying earlier that you can't assume that this is equal and that's just utter nonsense. Of course you could multiply by sine x times 1 plus cosine x to get that. And we know that's true because this is true. But if this is true, that's true. And then we divide this by sine x times 1 plus cosine x to get that. And if we were trying to solve an equation, 2x plus 1 equals 5. 2x is 5 minus 1 or 4. X is 2. All you've shown so far is that if there is a solution to the equation, it has to be x equals 2. When students are learning to solve equations, they should then check that in fact x equals 2 does satisfy it. But after they get a little more sophisticated, they should realize that any step that's reversible is okay. And the same thing is true with respect to identities. So, you didn't know how to do this as the authors of this textbook suggested, which was multiply and divide by 1 plus cosine x. And so you did it this way. And then you're not done. And students should be told, after they have proven this identity by working on both sides, they have learned something in the course of it. You should then go back and start on just one side, take the side that's more complicated, and try to change it into the other side, because that's the real problem that you're trying to learn how to do. That's the advice that should be given to students. The advice that's given here is wrong mathematically and it's wrong pedagogically. It's not dealing with the problem that students are really trying to learn how to solve. And I have yet to see a book that really explains that in enough detail. The one that my son used when he was in high school in pre-calculus by Fisher and Sieber comes very close to that. So that's some comments about textbooks. I'm very sorry I'm not here to answer questions and elaborate further. There's a lot more that could be said. I hope I'll get a chance to meet a number of you at future meetings in Chile or elsewhere. Thank you very much.